Good morning, all y'all. Oh, that's subtitled correctly. Yay! That one didn't. Morning brain fog. Are you in a brain fog this morning? Why is it brain fog 1? Like, why the 1? Morning, JR. Good morning, Joey. Someone already, so brain fog was taken, so you went with the 1? That makes sense. That's great. At least you're not like brain fog like 5,251. I call him Joey because that's his name. Joey was a student last semester. So, I mean, I can call him Minucci. Is that how you say it, Joey? Minucci? No, I'm missing letters. Joey's easier to say. That was close. Okay. Like I said, I think I'm missing a syllabus somewhere in the middle. Happy Wednesday. You guys survived all the Xi books. I am impressed, very impressed with all you guys have done already this semester. I mean, say what you say about remote learning, but this has been probably the highest participation in terms of in terms of the assignments that I've had since like this is my 4th semester teaching this class. 3rd semester? Let me see. 4th time teaching this class. So I'm very impressed with everything you guys have done. Keep up the good work. You got this. 1 week at a time. Any big questions before we get into lecture today? It's week 4. We're almost, I mean, next week will be a third of the way through the semester. You guys should celebrate. You guys should celebrate this weekend. Do something fun. Responsibly, of course. Buy yourself some ice cream. Yes, so JR, I stupidly forgot to look at your guys' quizzes on Monday, so I looked at them today. And a lot of people had questions on indexing and creating arrays. So I put together a whole list of things that you guys should be thinking about. And I mean, obviously, as you get more practice, it will be easier. But yes, I'm going to wait until class starts to go through those. So Zanzib, traditionally there are 16 weeks in a semester. You've got 1 week of break and then 1 week of finals. So there's 14 weeks of instruction. Our break already occurred. It occurred the first week because of, wonderfully made decisions by certain people that we will see the consequences of. So there's 15 weeks total straight that we have, 14 of instruction and 1 of finals. So it's going to be long. So make sure you guys schedule like little wins and like celebrations in there. You will still have weekly homework when the project is assigned. So you're still going to have weekly homework when the project is assigned. It's going to be linear algebra homework, though. So it's going to be math homework versus programming homework. We are going to completely finish all of the programming material by the midterm. And then the midterm essentially is, after that, is when you're going to really start working on your programming project. Yes, JR, I wish they sent an e-survey out for what instructors wanted as well. They didn't. I don't know how they made that decision. We were just told, as you guys were, that this is how it's going to be. And we get to live with it. So yay. But you know what? We're in it together. We can do this. Let me know where you guys are at. Let me know where you guys need help. I want to be on your side. I am on your side. I shouldn't say I want to be on your side. I am on your side. I want you guys to ultimately learn this semester. And I want you guys to be able to do that the best that you can. So, you know, let's work together. Okay. Class time. Let's go ahead and start. Okay, so I looked at your guys's, here we go. I looked at your guys's quizzes. No, come on. Work for me. Come on, capture card. There we go. Okay, so I looked at your guys' quizzes, and there's a lot. Okay, if you are still struggling with arrays and matrices and vectors and indexing and all of that, it's completely understandable. There's a lot of material that we went over last week, and I didn't even show you guys that much. I'm not necessarily happy with the way last week went in terms of me delivering content, but the problem is there's just so much. There's so much that I can't even cover it all. So I kind of, you just got to play around with it and see how it goes. So some of you guys mentioned understanding the difference between when to use brackets versus when to use parentheses. So we use brackets when we create a new array. That's essentially when we use brackets. When are you creating a new array? You're grouping together numbers so that they are in consecutive spaces next to each other. So 3, 2, 1. You would create a new array. Parentheses are used a couple different ways. One, they're used to group together mathematical operations. So just like if you're doing 3 times 2 divided by 7 times 5, you would group together the bottom ones. You can also group the top ones, but you would use parentheses. Say, do this operation first. They're also used to index an array. So when you're trying to talk about part of an array, so you would say A, open close parentheses, and then indicate which locations you want to access, you want to index. And then they're also used to send inputs to a function. So when we use a function, we would type the name, and then we would send it some data. So there's a couple ways we use parentheses. But brackets, they're used to create an array. That's the main way you would use brackets. Okay, so that's one of the things I wanted to review. Another thing I wanted to review is essentially the process of creating arrays and modifying them. Think about it as asking yourself a bunch of questions. So, first question, are you creating a new array? If you are creating a new array, that's easy. You just say A equals, and then you give it the values. Once again, you can use brackets if you're typing in the numbers, if you're concatenating things. So keep in mind, commas put things next to each other. Semicolons put things on top of each other. So if you're putting single numbers in, scalars, you just say value, comma, value, comma, value, or value, semicolon, value, semicolon. You can put rows on top of each other, row vectors on top of each other. You can put column vectors next to each other. Just keep in mind, if you are putting things next to each other, they need to have the same number of rows. If you're putting things on top of each other, they need to have the same number of columns. Second question. So if you're not creating a new array, are you modifying or trying to change an existing one? If you are, then this essentially is what you're going to be looking at. Here's the array you're trying to modify or change, and here's what you want to change it to. So first question in that, what do you want to modify or change? Which locations? Is it a vector? Then you just see one number or a series of numbers. Is it an array? You need the rows and columns. So we're asking what goes on my left-hand side. So if it's a vector, you just have A, open close parentheses, and then if you want to, you can always put in brackets to indicate that you're talking about multiple locations. You can put in one location, you can put in 2 locations, 3 locations, 4 locations. It doesn't matter how you create this array in here. It doesn't matter how you identify which locations you want to access, as long as they're integers. You can't have location 1.5. That just doesn't work. It doesn't work. If you're indexing a matrix, same thing. You would say A, open close parentheses, but now you have 2 arrays. So you can put a set of brackets here, comma, set of brackets here. Which rows are you talking about? Which columns are you talking about? So that all goes into what goes on to the left-hand side. What do you want to modify? What do you want to change? Which locations inside of the array? Once you know that, then you can go ahead and focus on the right-hand side, asking, what do I want to change it to? What do I want to store there? That's what that says. Hopefully you guys can read my handwriting. I used to have beautiful handwriting. Beautiful being relative, but beautiful handwriting. And then I took physiology in college and wrote down everything, and it just destroyed my handwriting. Do you use linear indexing to modify the array only? So linear indexing, so you use indexing to identify which locations you want to change, but you can also use it to on the right hand side. So Zanzib, I think this next thing will answer that question. So once you know which locations you want to change, you can also then figure out what goes on the right hand side. So what do you want to change it to? What do you want to store there? Are they new numbers? If they're new numbers, then you can literally just put in a scalar value or a new array of values. However this is, you can use the colon operator. You can say 1, 2, 3, whatever. So then you just create your new array of values. Or do they come from another array? If they come from another array, then you need to use linear indexing to identify which locations. It could be the whole array, where you could just say, I don't know, A, 1 through 3 equals some new array, some B. Or it can come from part of an array, where you can give it, once again, which locations, or which rows, and which columns. So on the right-hand side, or on the left-hand side, you're identifying what do you want to modify, what do you want to change, where are those locations, which ones do you want to be different. And over on this side, you identify which numbers do I want to put there. It doesn't matter where those numbers come from. They can be scalars. A scalar will just be repeated in all the locations. It can be a completely new array that you've created. It can be from another array that you're indexing. Zanzib, I think that answers your question. If it doesn't, let me know. So there's a lot to keep track of. Another thing that I think is really useful is writing out an example. So here is, I'm going to go through an example of homework 3, problem 3. So I think it's the corners one. So the corners function. Let's say we have a matrix that is a 6 by 5. So a 6 by 5 matrix, 6 rows, 5 columns. Okay, that's our input. A equals a 6 by 5. And then what if n is 2? If n is 2, I want this, 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 and this. Oh my gosh, I'm so sorry. And this. So those locations would be A, rows 1 and 2, and columns 1 and 2. And then it would be A, 1 and 2, and then these ones would be 4 and 5. And then A, 5 and 6, 1 and 2, A, 5 and 6, 4 and 5. Those are those locations if n is 2. If n is 3, then I want this one. These, these, and these. So A, 1 through 3, 1 to 3. A, 1 to 3, 3 to 5. And then A, 4 to 5, 1 to 3. A, 4 to 5, 3 to 5. And then you just keep going. So let's say, usually you can kind of get a feel after 2 examples, but go on to 3. What if n is 4? I want this one, this one, this one, and this one. So same idea. A, 1 to 4, 1 to 4. A, 1 to 4, 2 to 5, right? A, 3 to 6. Oops, this one should be 6. 3 to 6, comma. 1 to 4. A, 3 to 6. 2 to 5. So pull out an example, write down what are some different scenarios, and then you can start to see some trends. So notice this one, this first one, is always 1 to n, comma, 1 to n. This second one, it's 1 to n, and then it's different. So this number is always the same. It's 5, and then this number changes. How does it change? How is it in relation to n? And then you just keep going through those patterns. Note, if you do work for a generic size array, it's not always going to be 5. So how do you change it to the 5? You need to use the end keyword because it's the last element. It's the last, in this instance, the last column. So it helps to write out examples on paper to match things up, to see how what you're actually indexing, if it matches what you expect. Okay. Hopefully that helps. Your homework's due tonight. If you're stuck, office hours, yeah, keep moving forward. Like I said, there was a lot. There was so much in week 3. So much in week 3. Sometimes you just got to play around with it. You guys are starting to have to deal with more challenging debugging issues. So just try something in MATLAB. Start small. See what happens. N equals E. That one? Start small. Try something in MATLAB. See what happens. Sometimes you just gotta make observations and make assumptions based on those observations. So if I do this, this happens, okay? Assume that if you do that again, the same thing will happen. Okay, so let's go ahead and talk about matrix division and systems of equations, because that is the stuff we need to cover. Examples. Okay, so on Monday, we talked about a lot of things. We did matrix addition, subtraction, multiplication. Oh, multiplication. So there are some videos, there's some supplementary video, or there is a supplementary video I made. The link is in the lecture section of week 4. There's a matrix multiplication supplementary video. I went through 2 more matrix multiplication problems so that you guys don't have to sit there and sift through the entire lecture to try and figure out where the matrix multiplication is. So I made another video that's, I don't know, 6 minutes long. It goes through 2 more examples that you guys might find useful. So please watch that if you want more examples for matrix multiplication. And we also went over element by element operations. So remember, the asterisk is matrix multiplication in MATLAB. Your dimensions, your inner dimensions need to match. If you get a matrix matrix multiplication dimension mismatch, that means your inner dimensions don't match. If you put the period in front of it, that means it's going to be element by element. We also have element by element division and element by element exponentiation. Okay, if you don't put the period in front of these, it's going to assume you want the linear algebra version of multiplication, of division, and exponentiation, which is just a form of multiplication. Okay, so let's get into the inverse and systems of equations. So we don't actually have division when it comes to matrix multiplication. We can't divide things. It doesn't make sense with matrices. Instead, we have multiplication with the inverse. So instead of it being division, we're going to say A inverse times something. Okay. Just like when you say 1 over 5 times 5, this is the same as saying 5 divided by 5, where this is the inverse. Joey, no. If you are using the dot multiply, then they need to be the same size, the same number of rows and the same number of columns, just like it is for addition and subtraction. So if you do the dot, then they need to be the same exact size, because it's element by element. So they need to have the same number of elements in the same orientation. So in order to do the inverse, we need to know some stuff. So first things first, we need to know what the identity is. The identity is just a square matrix, square meaning that it has the same number of rows and columns, with ones along the diagonal, and then zeros everywhere else. So this here is the 4x4 identity. In MATLAB, you can create the identity using the I function, and you can just give it whatever size you want. So I4 would create this matrix. So let me erase that. I don't know why I keep erasing things. But if I want to say I2, so this one, that means I'm going to have ones along the diagonals and zeros like that. Identity is essentially the equivalent of 1. So if I do m times identity, it's going to look like this. Here's m defined here. So 5, negative 2, whoops. Come on. 1, negative 3 times my identity. So here I have a 2x2 times a 2x2. My inner dimensions match. My result is going to be a 2x2. So that means I have 4 dot products to perform. So row 1, column 1, 5 times 1 plus 0, which is 5. Row 1, column 2, 5 times 0 plus 1, which is 1. Row 2, column 1, negative 2 times 1 plus 0, which is negative 2. I'm not showing you the work because I really don't care about the work. I care about the answer for this example. Row 2, column 2, negative 2 times 0, minus 3, or minus 3. So notice, if I take a matrix times the identity, so m times the identity, I get my original matrix back. This is m. This is m. Okay, so that's what identity is. Which means that if I take a matrix times its inverse, so if I take m times m inverse, I'm going to get identity back. And you can double check your work using that. You can also double check your work using MATLAB. JR, we're not going to get into the theory behind things in this class because it's not a math class. There is practical applications, like practical meaning behind matrices, behind vectors. That's more what you see in physics. We are more interested in the calculations and not so much interested in what is actually happening from like a physical perspective. Because it's different depending on your application. Okay, so let's go ahead and calculate the inverse. Let's figure out how to calculate the inverse. So my equation for inverse, so m inverse, is going to be 1 over the determinant of m times m adjoint, or adjugate. Same thing. Right now in week 4, we are going to focus on 2x2s. There's a good series on linear algebra on YouTube by 3 Brown 1 Blue, I think is his name. Yeah, to him. That he goes into like all the visual aspects of linear algebra, which is really awesome. So if you are interested, go watch his series on linear algebra. Because he has like all the visuals on what is actually happening. Because when we're talking about linear algebra, and we'll see this later on, we're really talking about lines on a coordinate system, and dots and all of that fun stuff. So like I said, that's the same. It's beyond the scope of our course just because we're trying to cover so much. And we're going to focus more on just the calculations and what it means to compute them in a program. Okay, so here's my equation. Here is my equation for inverse. Like I said, we are going to focus on a 2x2. We're going to get more into determinants and how to calculate the adjoint for bigger matrices later on in the semester. We're going to focus on 2x2s, so I'm going to focus on how to do it for a 2x2. So first things first, we need to calculate the determinant. The determinant of m. For a 2x2, it's actually really simple. It looks like this. So if m is 5, -2, 1, -3, I like to draw a little fish. I'm going to multiply these two numbers together and multiply these two numbers together and subtract the 2. So it's going to be 5 times -3 and then -2 times 1, and then I'm going to subtract them. So I like to draw a little fish that indicates multiply these minus the multiple of these. That's how you calculate the determinant of a 2x2. So this is going to be -15 plus 2, -13. So here we go. Here's my determinant. The determinant of m equals -13. If you look at this equation, over here, any determinant value is valid except for 0. So as long as m is not 0, then I'm fine. I can move forward with my calculations. So I've calculated the determinant. That's great. I'm almost done. That means the only thing I need to calculate left is my adjoint matrix. Once again, to calculate the adjoint matrix for a 2x2, it's actually pretty simple. First, 5, -2, 1, -3. First, these two are going to switch places. So the -3 and the 5 are going to switch places. And then I'm going to change the sign on the other two. So my 1 is going to become -1, and my 2 is going to become +2. And that's it. These two switch places. These two change their sign. Once we have the adjoint matrix, or adjunct matrix, I can go ahead and put it together. So m inverse is going to be 1 over -13 times my adjoint matrix, or times this. Notice this is a scalar. This is a matrix. You can just multiply through. So technically, I should say it's -3 or 3 over 13, 1 over 13, -2 over 13, and -5 over 13. There we go. Pretty straightforward. You'll remember it as you do more. So let's do another example. Let's say we want to find n inverse. Same formula, 1 over the determinant of n, and adjoint. My determinant of n is going to be, so if n looks like this, from up here, 3, -3, 5, -2, the determinant, I draw my little fish, 3 times -2 minus -3 times 5. I use my fish to remind me how to do it. So that gives me -6 plus 15, or 9. And then n adjoint, notice 9 is not 0, so I can still move forward. My adjoint matrix, the 3 and the -2 switch places, and then the -3 and the 5 change their sign, so it's -5 and +3. Now I can put it all together. 1 over 9 times my adjoint. If I simplify that, I get -2 ninths, -5 ninths, 1/3, and 1/3. That's it. You just keep moving through, just practice. Find the determinant, find the adjoint matrix, multiply together. If you want to check your work, you can go ahead and use MATLAB, just like you can for everything else. Check it with MATLAB. You're not inversing the determinant. You're using the determinant to find the inverse. Did I? So that's, Joey, that's your formula. That's your formula. So here's your formula. So it's 1 over the determinant. Okay, let's check our answers. Hopefully I did all my math correct. Go back to MATLAB. Okay, so M and N look like this. Here we go. There's a couple ways to calculate the inverse in MATLAB. You could just do M raised to the -1. That will give you the inverse. Notice it gives you decimal places. If you want fractions, you can type format rational. This is a really nifty trick that one of my students actually showed me like 3 years ago. Format rat if you want fractions. World of a difference in this class. Format rational. So now I can recalculate M inverse and it will give me the actual fractions, which matches what I got, which is great. Okay, so that's one way we can calculate the inverse. You can also use the inverse function, or INV, in order to calculate it. So inverse of n. Same thing, gives you the inverse, -2 times 9, 1/3, -5 over 9 and 1/3. Same thing what we got. If you want to calculate just the determinant, you can use the DET, or determinant function, and you can double check your answers for your determinant. Okay, and that's true for any size matrix. So these formulas, the way to calculate these is true for any size matrix. Like I said, we are going to focus on 2x2s by hand right now, but this works for any size matrix. So I could say I could say A equals rand I 10 by 10. So here's a 10 by 10 matrix. I could say determinant of A. It's really large, that's fine, and inverse of A. Okay. So these equations work for any size matrix, okay? But we're gonna focus by hand for a 2x2. Keep in mind, the inverse and the determinant can only be calculated for square matrices. Okay, so these only work for square matrices. So if you're trying to calculate the determinant of a 3x2, you can't. Okay, so like I said, there's no division, there's no explicit division in matrices. Instead, we multiply by the inverse. So there's two ways we can have division. There's right division and left division, which is just either a / or a \. So here's our normal division. This is right division. If we say M divide N, M right divide N, we are effectively doing this operation in MATLAB. We are taking M and we are multiplying it by the inverse of N. So that operation is just matrix multiplication. So M looks like this: 5, -2, 1, -3. And then N inverse is what we calculated. -2, 9, 1/3, -5, 9, and 1/3. So it's just matrix multiplication, just like we did before. Here's a 2x2. Here's another 2x2. Inner dimensions match. That's great. My outer dimensions tell me how big my matrix is going to be. It's another 2x2. So I do 4 dot products. Row 1, column 1. Row 1, column 2. Row 2, column 1. Row 2, column 2. Notice you're dealing with fractions, which is why in MATLAB you want to have format rat, so you can double check your work. You also don't have to multiply by the determinant through. You could also write this like this, times 1 over 9 -2, -5, 3, 3. If you want to work with whole numbers and do the division last, this is also completely fine. It's up to you. I like to work with whole numbers, so I'm going to do it this way. So I have 1/9 times, okay, my first dot product. Here we go. 5 times -2 plus 1 times 3. And this one. -2 times -2 plus -3 times 3. And then this one. 5 times -5 plus 1 times 3. And then this one. -2 times -5 plus -3 times 3. And then you can simplify through. Okay, so sometimes it helps if you don't end up with whole numbers in your inverse, which most of the time you don't, or a lot of the times you don't, unless we give you well-crafted numbers. It might make sense, it might help to just leave it like this, because this is completely valid as well. It's nice that you have scalars. You can kind of move them about a little bit easier than matrices. Okay, and then you can also check your work with MATLAB. You can say m right divide n. Same thing as if I typed m times n inverse, or m times inverse of n. All the same answer. So that's 3 ways to type the same operation in MATLAB. Okay, so that's right division. That's our normal division sign. We also have left division, which you guys will get very used to because we're going to use it to solve systems of equations, and we'll see why. So if you do m left divide n, it's your /, it's the one right underneath backspace, you're actually doing this. You're taking m inverse times n. So note, depending on which direction your division sign is, tells you which side is going to be the inverse. So it leans this way, which means this side is going to be the inverse. It leans this way, it means this side is going to be the inverse. A nice trick I just came up with myself right now. Okay, so same thing, we just take m inverse. So m inverse was over there, 1 divided by -13 times 3, 1, -2, 5, -5. So there's m inverse times n. And looks like this, 3, 5, -3, -2. And you just do that multiplication. Same thing, 1 divided by -1/13 times all of your dot products. So 3 times 3 plus 1 times -3. -2 times 3 minus 5 times -3, or plus -5 times -3. Keep going. 3 times 5 plus 1 times -2. This one. And then -2 times 5 minus 5 times -2. This one. And then you can continue and simplify. So it's really crucial that you understand matrix multiplication, because it shows up in all of these operations. It shows up in multiplication, it shows up in division, right divide, left divide, and matrix exponentiation. So keep in mind, matrix multiplication, it can be used for any size matrices as long as the inner dimensions match. These ones only apply to square matrices. Okay, that's the inverse. That is the inverse. And that's fine, that's all fine and dandy. However, the main application for this class, at least, as to why we even care about this, other than the fact that that's what happens inside of MATLAB, but the main application for all of this is we want to utilize linear algebra in order to easily solve systems of equations. A lot of what you do in your upper level courses, solving for unknowns, solving for something, utilizes systems of equations, and you've seen them before. This is an example system of equation. So these are all example systems of equations. Here's your basic one you've seen probably in algebra class. Here is a basic one. Oh, that was from a video. Here's one from circuits, actually. Some of you guys might be in EAS 200. So here's a system of equations that you can develop from a circuit. And here is a system of equations that you may have developed or can develop from a statics problem. Okay, so these are 3 examples of systems that are a little bit closer to where you are currently in your academic path. But also, as you get further on, you're going to be developing even more extensive systems of equations. So we're going to go through how to easily solve systems of equations using MATLAB without having to do a whole bunch of algebra. So NutJev, it depends on your application. It depends on what you're trying to do, what you're trying to solve for. We are going to, so we don't typically use this one in this class. But we are going to use this one because this is how we are going to solve these systems of equations. And I will show you that in about 3 minutes. That's a good question. So it just depends on your application, what you're trying to do. Okay, so let's look at this first system of equations. So I've got 2 equations and 2 unknowns. Turns out we can write equations in what's called matrix form, where we're going to have an A matrix, an X matrix, and a B matrix. So A is going to be full of our coefficients in front of our unknowns. X is going to be full of our unknowns. And B is going to be full of our constants on our right-hand side. A is going to be structured in a way where each row corresponds to an equation. And each column corresponds to an unknown in the equation. Like I said, X is full of our unknowns, so it's going to be full of our letters. So X, Y, Z, maybe it's X1, X2, X3. It doesn't matter. It's full of our letters. And then B is everything that shows up on the right-hand side, once again, following the equation. So the right-hand side of equations. Okay, so like I said, that's how it's set up. Let's go through an example. I'm just going to move this over to the side. So we have space. Okay, so if I look at this system of equations, I have 2 equations, 2 unknowns. That means A is going to be a 2 by 2. The first row is from equation 1, and the second row is from equation 2. My unknowns are X and Y. So that means I can put this in any order, but column 1 is going to correspond to X, column 2 is going to correspond to Y. So now I'm just going to fill A according to my equation. So if I look at equation 1, the coefficient in front of X is -2. The number in front of X here is -2. For equation 1, the number in front of Y is 1. For equation 2, the number in front of X is 4. The number in front of Y is 1. There we go. I filled A. Row 1 is from equation 1. Row 2 is from equation 2. Column 1 is the number in front of X. Column 2 is the number in front of Y. Okay, so there's my A matrix. My X matrix is full of my unknowns. So don't get confused between this X and this X. X is a vector. So A, X equals B. This is just a generic name for a vector that's full of your unknowns. It just so happens the unknowns in my system of equations are X and Y. So I'm going to put X and Y because X corresponds to column 1 and Y corresponds to column 2. And then B, once again, is just a vector. It's going to be the numbers on the right-hand side. So 5, -2. There we go. I have my equations in matrix form. The hardest part is putting A together. So here's A. But once again, row 1, equation 1. Row 2, equation 2. Column 1, first unknown. Column 2, second unknown. If you actually did this matrix multiplication, you would end up with your original system of equations. So if I actually multiplied these two matrices together, I would get a 2 by 2 times a 2 by 1. Match. My result will be a 2 by 1, where I have dot product, -2x plus y, dot product, 4x plus y, equals 5 and -2, which is my original system. So that's the math. That's just double checking to make sure our equation is correct. So I've got it in the form of ax equals b. Let me clean everything up a little bit. It's a little messy. Come on. In order to solve this equation, it turns out my equation is just going to be A inverse B. So I multiply both sides by A inverse, and I get A inverse times B. This is my solution. In MATLAB, I can type it as x equals A left divide B. So Nachav, this is where you would have that example of why you might want to use left divide, because this is how you can type it in MATLAB. It's really simple to type, which we know is just A inverse times B. So I can find A inverse. A inverse is going to be 1 over the determinant of A times A adjoint. Once I find that, I just multiply it by B. So if I do that, it's going to be 1 over -2 minus 4, or -6. Adjoint is going to be 1, -2, -1, -4. B is just this vector here, 5, -2. It's just a matrix multiplication. A 2 by 2, come on, times a 2 by 1. So my result is going to be a 2 by 1. Dot product, 5 times 1 minus 1 times -2. Dot product, -4 times 5 minus 2 times -2, or plus, and then 1 over -6. Don't forget my 1 over determinant. So that means that x equals, if I do this math, let me do it in MATLAB. 5 plus 2, 7, -7 sixths. And then 20, -20 plus 4, 16. So -16 over 6, or simplifying that, 8 over 3. So that means this is my first unknown, so that's x, and this is my second unknown, that's y. So if I plug this in for x and this in for y, I can check that my system of equations is solved. This is a lot, and I spread all over the page. There's a lot here. I should probably clean it up a little bit. I will create another supplementary video. So Joey, I'm gonna say no right now, and I will create another supplementary video that goes over solving 2 more systems with 2 by 2s. that explains that a little bit more. I do want to go through how to solve things in MATLAB and setting up a bigger system of equations, because you will have to do that on your homework. So, how do I... Can I just like press enter a million times? Yeah, let me let it catch up. Sorry, I'm trying to just clear out some of the space without deleting it. Okay. You can stop now. So here is another system of equations. So note, here I have 4 equations. And I have 4 unknowns. My unknowns are I1, I2, I3, and I4. Like I said, those are my letters. So I1, I2, I3, and I4. Not every equation has every unknown, but that doesn't matter. But we just need to keep track of how many unknowns do we have. For our purposes, for the most part, it's going to be 4 equations, 4 unknowns. 5 equations, 5 unknowns. 2 equations, 2 unknowns. 10 equations, 10 unknowns. But either way, we can write it in the form of ax equals b. So a is going to be filled, once again, with my coefficients in front of my unknowns. So if it's a 4 by 4, that means I'm going to have 4 rows from equation 1, equation 2, equation 3, equation 4, and then 4 columns. Yes, you're right, Luke, it is positive. My bad. So here, this first column is from my first unknown, second unknown, third unknown, fourth unknown. So here I'm setting up A. So for my first equation, the value in front of I1 is 32. So that goes here. The value in front of I2 is negative 16. That negative stays with. The value in front of I3, there's no I3 in this equation, which means it's just 0. Same thing for I4. There's no I4 in the equation, so it's just 0. For equation 2, the number in front of I1 is negative 6. The number in front of I2 is 42. The number in front of I3 is negative 12. The number in front of I4 is negative 14. My third equation, the number in front of I1, there's no I1, which means it's 0. The number in front of I2 is negative 12. The number in front of I3 is 24. The number in front of I4 is negative 4. And then for my last equation, there's no I1, so it's 0. In front of I2 is negative 14. In front of I3 is negative 4. In front of I4 is 23. So it helps to set up your matrix like this. Your X is your unknowns. I1, I2, I3, I4. Just literally take these values and throw them in. Your B, it's the vector of everything on your right-hand side. From equation 1, it's negative 28. From equation 2, it's 0. From equation 3, it's 36. And from equation 4, it's negative 42. There we go. I have set up this system of equations. 4 equations, 4 unknowns, set up A, set up X, set up B. In MATLAB, if I wanted to solve this system, it just looks like this. So A is typed out like this, just exactly how I typed it or how I wrote it. B, same thing. It's typed out exactly how I wrote it. We can't type out X. We can't say, or I, whatever you want to call it, we can't say X equals I1, I2, I3, I4. We can't do that. It's going to give us an error. Because we don't know what X is. We are solving for X. It's an unknown. So we can't type X into our MATLAB. We type in A, we type in B. And then we solve for X. The way we solve for X is we can just say A left divide B. This is A inverse times B. You can call X whatever you want. I call it I because there's a bunch of I's in it. So now here's my answer. If you don't want fractions, you can just go back to format. Just type format, it'll go back to fractions. So this here, this first number is I1. This second number is I2. This third number is I4. And this third number is I3, and this fourth number is I4. So now I can go back to my sheet of paper and I can type out, or I can write out that I1 equals negative 1.178, I2 is negative 0.6, I3 equals 0.8, and I4 equals negative 2.0457, whatever, however many decimal places. There we go. I didn't have to go through a whole bunch of stuff. All I needed to do was take this equation, write it in the form of Ax equals B, type it in MATLAB, and it gave me the answers. And that is all the time we have, but I want to set up this one if you have like 2 minutes. I mean, I don't know where you're going to go. I'm going to be late for office hours, but okay. I'm going to set this one up still. So here I have 1, 2, 3, 4, 5, 6, 7. So 7 equations, which means I should have 7 unknowns. My unknowns are F's. So it's F1, F2, F3, all the way to F7. So if I set up A looks like this. 1, 2, 3, 4, 5, 6, 7. And then I have F1, F2, F3, F4, F5, F6, F7. So here's A. So now I can fill it in. For my first equation, F1 is cosine 30. Don't bother about actually finding out what it is. Just type it in. In front of F2 is 1. There's nothing else. So it's 0, 0, 0, 0, 0. For equation 2, it's just sine of 30. And then 0, 0, 0, 0, 0, 0. So this equation, it would be easy to solve for F1. Don't even worry about it. Just type it in. And then you just keep going. So negative cosine 30, 0, negative cosine 60, 0, cosine 60, cosine 30, and then 0. So you would write in every single equation. X is your F1 all the way through F7. It honestly doesn't even matter what you write for X right now because you can type it into MATLAB. And then B is everything on your right-hand side. From equation 1, it's 300. From equation 2, it's negative 6467. Then negative 3,000. Sorry, I meant 3,000. Then 0, then 0, then negative 7533, then 0. Regardless of what it is, you set it up. You go back to MATLAB. You type it in. Notice I just typed in the cosines. Also notice I kind of spaced things out so you can easily double check to see that it matches your pieces of paper. So it doesn't matter how many spaces there are between numbers. It just matters that the number of numbers in each row is the same. So this is what A looks like. This is what B looks like. And then F equals A left divide B. So that's a really good question, Aurora. For this matrix, it's actually easier to type in all those zeros because you would have to index A 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Like there's 17 additional numbers to put in. So for this matrix, it makes sense to just type them in manually. For other matrices though, and for your programming project, you're gonna set up a system of equations that has a matrix that's filled with zeros with like values along the diagonal. That's where it would be much easier if you started out using the zeros function and just say A equals zeros, 7 comma 7, and then you could fill in each row. So A, row 1, columns 1 and 2 equals cos D 30 comma 1. And then you can fill it in row by row. So it really depends on how big your matrix is and how many zeros you have and how many non-zeros you have. That's a really good question. Okay, but regardless, for our systems, you essentially set up A, you set up B. If it's not a 2x2, you don't know how to solve it yet by hand, so just plug it into MATLAB. It's literally just one line of code. It will solve everything for you to where this is your first number, second number, third number, fourth number. If you ever run into the situation where you have 1e to the fourth, that means it applies to all of these numbers. If you want to get rid of that, just type format short G. Learned that a couple years ago. And then, whoops. Sorry, I redefined A. And then it will give you all those numbers. It just because there's a wide range between values. Okay, I am way over. I am sorry, but I thought this was relevant. I thought it'd be important. I need to jump to office hours. Are there any final questions before we head out for the week? For this class, at least. Okay. I will see all of y'all next week. Keep up the good work. You got it. And I will post that supplementary video on solving 2x2 systems by hand. We just didn't have enough time today because I really wanted to show you guys how to write bigger systems because you will have to do like a 17x17 in your homework. Okay, with that, I will see you guys next week.